So we have another example problem here where we can use conservation of energy. So desperate contestants on a TV survival show are very hungry. Only food they can see is some fruit hanging on a branch high in a tree. Fortunately, they have a spring they can use to launch a rock. The spring constant, 1,000 newtons per meter, and they can compress the spring a maximum of 30 centimeters. All the rocks on the island seem to have a mass of 400 grams. Well, that's just convenient, right? So if I have this rock on my spring, now remember with springs, we must know where equilibrium is. So I'm going to draw a line representing the equilibrium of this spring. So to launch the rock, they're going to push the rock down into the spring to make it coil up tightly. When they let go, the spring force will push that rock upwards. So first we want to know with what speed does the rock leave the spring. So if I'm representing my initial moment in time as we've pushed this rock down on the spring as far as we possibly can, our final moment in time needs to relate to the question I'm trying to answer. So I'm trying to answer, well, with what speed does the rock leave the spring? So I know the spring will keep pushing on the rock until it leaves the spring with some final velocity here. So my final moment in time, the spring is back to its original equilibrium state. Equilibrium. The V final is how fast the rock will be traveling. So our potential energy plus kinetic plus work external is equal to potential plus kinetic plus thermal energy. We do not have that thermal energy generated, at least not in the form of kinetic friction. Technically, there's going to be some thermal energy generated within the spring, but we're not going to worry about that. We're going to just assume that doesn't occur. In terms of the forces acting on the rock, we have the spring and gravity. So that means we do not have any external forces that would be either adding energy to this system or removing it. So we can say that the initial potential and kinetic energy has to equal the final potential and kinetic energy. In this case, though, we need to consider both gravitational potential energy and spring. The reason I know I need to consider both, well, number one, there's a spring. In terms of gravitational potential energy, I know this rock is changing height. Therefore, I need to account for gravitational as well. So initially, the spring is compressed. When we talk about spring potential energy, that S always needs to be how far the spring is compressed or stretched at that moment in time. And so, that S initial is the 30 centimeters that we can push the rock down into the spring, that maximum compression. Now, gravitational potential energy, mgy, we can choose y to be 0 wherever we want. Oftentimes, it's nice to choose it at the lowest point, though we could totally put y equals 0 at that equilibrium and then y initial would just be negative, that's fine as well. But moving forward with u gravitational, if I'm calling that lowest location y equals 0, then I'm defining the potential energy due to gravity to be 0 there. The kinetic energy is also going to be 0 because we've compressed it. We're just going to release it. So that initial, right before we release, the speed is 0. At the final moment in time, so meaning the rock is leaving and it's being launched from the spring is no longer stretched or compressed. So the spring itself no longer has energy, or is not contributing energy to the system, I should say. Gravitational, the rock is now higher than it was before. It's 30 centimeters above where it started. And so we will have gravitational potential energy at that moment. And the rock, of course, is moving, so there will be kinetic energy at this moment. So our conservation of energy equation simplified down to be just potential plus kinetic. Initial, so all of this initial stuff, which is essentially just 1/2 k initial squared. Initially, that moment in time, all of the energy is because of the compression of the spring. Our final moment in time, some of the energy is in gravitational potential energy because of what gravity is, how gravity is acting on this rock. And some of the energy is kinetic. Excuse me. So this here, for this specific situation, is our symbolic equation that we would be working with. That is specific to part A. Okay. We want the speed, so we want V final. We have K, that's the 1,000 newtons per meter. We have S initial, the 30 centimeters. We have the mass of the rocks, but we'll want that in kilograms. We know G. We know Y final is the 30 centimeters, which we will want in meters. So we have everything we need in order to solve for V final. So bringing mg y final over, and then I'll multiply by 2, divide by m. That will leave me with v final squared. So I will want to take the square root of both sides. .3. So remember to put these distances in meters. Mass in kilograms. Plugging these numbers in. I'm getting 14.8 meters per second. So approximately 15 meters per second. So that's the answer to part A. Excuse me. Part B is telling us that the fruit hangs 15 meters above the ground. So will these contestants be able to eat, assuming they hit the fruit, or not? So essentially, will this rock even go high enough to hit the fruit? So coming back to our picture, I can still keep this same initial moment in time and just choose a different moment in time where the spring is still just here, the rock has gone as high as it can, so it's at its maximum height. If this is my new final moment in time, the spring doesn't have energy, it's not attached to the rock, so it does not get stretched out. We do have gravitational potential energy because that rock is up a vertical distance. At the maximum height, there will be no potential energy, kinetic. So all of the energy the spring has initially, and by spring, I really mean the spring rock system. So all of the energy that exists in the system because the rock is pushed down and compressing the spring, all of that is going to turn into gravitational potential energy. That's what this is telling us. It doesn't tell us anything about in between. It's not telling us the speed because we skipped the moment in time where the rock was leaving the spring. But that's okay. Energy is wonderful in that we don't have to break it into pieces, into parts. We can simply just look at 2 moments in time as long as we are accounting for all the types of energy, then we're good, which is really nice. So here we can find Y final. This is going to tell us how high the spring can go. The rock can go because of the spring's force. Now, total side note really quick. I hope you know within the potential energy, this is the spring constant. Don't confuse that with kinetic energy in our conservation of energy equation. 2 Ks. The spring constant is technically a lowercase k. Kinetic energy is capital K. So plugging these values in, I'm getting 11.5 meters. This is how high above the compressed position of the spring. That the rock will travel. Because we chose y equals 0 to be that lowest point. Well, that's still a good 3.5 meters below where the fruit would hang. I'm assuming our spring itself is not 3.5 meters above the ground when it is fully compressed. So these people are going to go hungry. The rock cannot go high enough to knock the fruit out of the tree.